So we're going to talk first about absolute extrema, sometimes referred to as global extrema. So you want to know both of those terms because both of those might be how they're defined on the AP test when they ask about them. So easy enough, you can think about an absolute maximum or an absolute minimum as the highest point on the graph or the lowest point on the graph. It has to be defined as a specific number, right? So we can't say infinity or we can't say negative infinity as the absolute max or the absolute min. Like, for example, if we have, a cubic function, right, that does something like this, well, the cubic function has no absolute max and it has no absolute min because it goes towards infinity and it goes towards negative infinity. So no absolute max or min. But an absolute max or an absolute min is just the highest point. So for example, or the lowest point. So you have a parabola, right, has no absolute max if it's opening up, if it's concave up, right? But it does have an absolute min. It has no absolute min if it's opening down, but it does have an absolute max. Easy enough. Hopefully. All right. Yeah. So from there, we will sometimes also restrict the domain of a function so that it does have an absolute max or an absolute minimum on an interval. And so what we're going to start with is we're going to start by taking a look at just a couple of simple trig functions, sine of x and cosine of x, and restricting their domains to 0 to pi. So let's look at cosine of x first. Maybe. Really like, there we go. All right. So let's talk about cosine of x on the interval from 0 to pi. Does it have an absolute maximum? Is there an absolute highest point on the graph of this from 0 to pi? Is there a highest point on the cosine function?
Yeah.
Yes, and it is 1.
It is 1. All right. There's an absolute max of 1. And where does it occur? At x equals?
At x equals 0.
At x equals 0. Perfect. And what about an absolute min?
-1.
-1. And that one occurs at x equals pi, right? Everybody good with that, right? That is the highest point and the lowest point. That should be hopefully pretty straightforward. What about the sine function from 0 to pi? Does it have an absolute max?
1.
It's also 1. Where does that occur?
Pi over 2.
Okay. What about an absolute min?
-1 at pi. I mean,
Right, just about the sine function, right?
0.
Okay, does it have an absolute max of 0? It certainly hits 0 twice, doesn't it? And that's okay. It has an absolute, I wrote max there. I'm going to fix that in a second. I don't know why I wrote max. It has an absolute min of 0 at x equals 0 and at x equals pi. And it's okay for the minimum value to occur at multiple places. That's why I would say this, these inequalities here with the or equal to. So we have an absolute max in the domain of our function if the function is always less than or equal to that value for all other values in the domain. And it's an absolute min if our function is always greater than or equal to that value. Right? So this is an absolute min because every other value of the function is either greater than or equal to 0 from 0 to pi. And same with pi. At pi, it's 0, and every other value of our function from 0 to pi is always greater than or equal to 0 on our domain. Does that make sense?
Yeah.
Okay, so it's important for us to recognize that a function on an interval might have, it only has one absolute max and one absolute min, but that absolute max or that absolute min might occur multiple times on the interval. So it's an important idea. Everybody good with that? Hopefully. All right, so let's take a look at the function f of x equals x squared, a nice simple parabola, and talk about the absolute max and the absolute min of it, given certain restrictions on the domain. So we'll start with the just standard domain of f of x equals x squared, which is from negative infinity to infinity, right? So in that case, this is just going up and up and up forever. What can you tell me about the absolute max?
There is no
Yeah,
absolute.
would there be none or would it be infinity?
There is no
None.
absolute.
Okay.
It has to be a specific value, has to be a number that we hit, and infinity is not a number, it is just the idea that these numbers keep increasing. And so there is no absolute max. What about an absolute min?
There's a
Min 0.
0.
Yep. So we have an absolute min of 0, and where does that occur?
X equals 0.
At x equals 0. Good. All right. Everybody feel okay about those on negative infinity to infinity? Hopefully. What if we change it to the closed interval from 0 to 2? So if I just talk about here to here, does it have an absolute maximum on that interval?
Yes.
Yeah, it's got an absolute max of
4.
4, and that occurs at x equals 2. And what about our absolute min?
0 at x equals 0.
Again, 0 at x equals 0. Cool. Now, what if instead of having a closed interval, we make it a half open interval? So rather than being closed at 0, it's open at 0, but it's still closed at 2. Do we still have an absolute maximum?
Yes.
Yep, should still be the same, right? Our absolute max should still be 4, and it's still occurring at x equals 2. What about an absolute minimum?
We don't have one.
We don't have one, right? Because we are getting closer and closer and closer to an x value of 0, which means we're getting closer and closer and closer to a y value of 0. But those values keep getting smaller, but we never get to a smallest number. We never stop, right? So there's no absolute min.
Could you define it as a limit?
I mean, we could not define the minimum itself as a limit because the minimum has to be a specific value that you actually obtain, whereas a limit is not something that we actually have to obtain. So they're sort of contradictory to each other there.
Oh, okay.
We would say that the limit as x approaches 0 from the right of this function is 0. Right? So we know that we're getting very close to 0, but we couldn't actually say that the minimum is 0 because we don't ever actually get to it. And what if I made this an open interval on both sides?
Do neither exist?
Yeah, we have no absolute max or min. Right, we're getting very, very close to a max of 4, and we're getting very, very close to a minimum of 0, but we never actually hit either one of those, right? Because we get very close to 2, which means we get very close to 4. We get very close to 0, which means we get very close to a y value of 0, but we never actually hit those exact values. And since we don't get to that actual numeric value, we can't state a max or a min there. Good or no?
Good.
Cool. All right, so which one, only one of those gave us an absolute max and an absolute min. Only the one that was closed on both sides. Can you think of any function that has a closed interval on both sides and that is continuous for that entire closed interval that wouldn't have an absolute max or an absolute min? So a continuous function on a closed interval that doesn't have an absolute max or min.
Sine and cosine.
So on a closed interval, let's close our interval wherever we feel like, it should still have an absolute max and an absolute min, right? Up here, it should still have a max of 1, and it should still have a min of 1, right? Because we've closed off this interval. It's guaranteed that it has one. Even if we, like for example here with cosine, we closed it off at its highest point and its lowest point, right? It's still got a max and a min. Suppose we stopped it here, well, it would still have a max and it would still have a min, right? It'd be different.
Could it be a flat line like y equals 5?
All right, so let's think about that. Get rid of all this here. Y equals 5, I can even draw that one on here, right? And let's close off the interval, right? Since we were talking about on a closed interval. Well, pick a value on there. How about this one where it's 5? Is that value of 5, and I'm going to switch to the other page for a second, is that value of 5 always greater than or equal to all the other values of the function?
Yes.
Is it always less than or equal to all the other values of the function?
Yes.
Yeah, so if we have a straight horizontal line on a closed interval there, the absolute max is 5 for this one, and the absolute min is 5, and they occur at every single point in the domain. So there still is an absolute max and an absolute min. In fact, there is a theorem that tells us that on a closed interval, if you have a continuous function on that closed interval, there will always be an absolute max and an absolute min on the closed interval somewhere. That theorem is called the extreme value theorem. So the extreme value theorem officially states if f is continuous on a closed interval from a to b, then f has both a maximum and a minimum value on the interval. Guaranteed. It will, no matter what, have an absolute max and an absolute minimum if it's a closed interval and if the function is continuous on the entire closed interval. Okay. So I've drawn 5 different little graphs up here, and we're going to quickly talk about each one. I didn't draw endpoints on these as closed endpoints, but just assume everything up there has a closed endpoint there on the end. For the first graph, does it have an absolute max? Should, right there, yeah. And it should have an absolute min right there. Would you guys agree with that?
Yeah.
Yeah, okay. What about the second one? Does it have an absolute minimum?
Yes.
Yeah.
Where's the absolute minimum?
8.
At A, right? And it has an absolute max somewhere between A and B up here at this little vertex looking thing, right? What about the third one there? Does it have an absolute minimum?
Yeah, between A
and B.
Between A and B.
And then what about an absolute max?
at B.
At B.
B. And then what about the fourth one up there? Does it have an absolute max?
A.
At
Yeah.
A, right? Not of A, but at A. And what about the min at B, right? What about the bottom one down there? Does it have an absolute max?
No.
No, it doesn't. It doesn't have an absolute min either, even though it is definitely defined on that entire interval. It's a closed interval from A to B, right? Every point from A to B has been taken care of, but it's not continuous. And so it's not guaranteed to have an absolute max or a min. But all the rest of them were continuous. And we would note that those absolute extrema could occur on the interior of the domain, like in the first one, or it could be at an endpoint and also at an interior point, like the next two, or it could both be at the endpoints. Right? Everybody good with that?
If the points at A and B for the last one, like let's say the point at A was below the function and then the point at B was above the function, would there be a min-max or no?
It would still have an absolute maximum and an absolute minimum on that value. Yeah, if like suppose A was down here and B was up here. Yes, it would still have them. And which is okay, because the extreme value theorem is only telling us that we are guaranteed to have one if it's continuous and if it's a closed interval. It's not saying anything about not having them if those conditions aren't met. So we could still have them, we're just not guaranteed to have them. For example, I could draw a function just like this first one, except giving it open intervals on the ends. And this still has an absolute max and an absolute min, right? Still hits the highest point and still hits the lowest point. So we can still have an absolute max and an absolute min if it's not a closed interval or if it's not continuous on the entire interval, but we're only guaranteed to have it if it's a closed interval and a continuous function.
Okay, thank you.
Yep. Any other questions or issues with that? Everybody okay there?
Good.
All right, let's move forward then. So now we're going to quickly talk about local extrema, local maxima, and local minima. And so the only difference between an absolute and a local means that an absolute, it has to be the highest point on that entire domain, right? The entire domain of the function or the entire piece of the function that we are specifically talking about. But a local one doesn't have to be the highest point on the entire domain of the function. It just has to be the highest point on some open interval around that point. So for example, let's take a look. Let's say how about the point at C? At C, I could define some open interval surrounding C, and it is the lowest point on that interval, isn't it? Would you agree with that? That's the lowest point on that interval surrounding C?
Yes.
Yes.
Hopefully so. Okay, cool. So that being said, it's a local minimum, but it's not the absolute minimum because the absolute minimum occurs at the endpoint at A. Okay? We could even do the same thing for endpoints. For example, at E, E is a local minimum because on the half open interval surrounding E, right, there is no points that are less than E, right? E is the lowest point. It increases as it goes towards the left away from E. Okay. Same idea here with this point at B. Point B is a local maximum. On some open interval surrounding B, it's the highest point, but it's not the highest overall point. That's at D, which is also a local as well as an absolute max. So any absolute minimum or maximum is also a local max or min. So this is local and absolute, whereas this is just local, this is just local, and this is just local. And so we'll note that both the absolute and the local minima and maxima can occur both on the interior and at endpoints. And we've already talked a little bit about when these local maxima occur, haven't we? When is one time when these local maxima or minima could occur?
In cubics or quartics.
Okay, yeah, so in third and fourth degree functions, and we dealt with a lot of those, let's say, when what was true about the derivative.
crosses the x-axis?
No, it doesn't have to necessarily cross the x-axis. It could do it at that point. But what's going on with the derivative at this local maximum or this local minimum?
Horizontal tangent line?
It's got a horizontal tangent line, which is telling us that the derivative equals 0. So we're going to use that idea that when the derivative is 0, it's a potential local maximum or minimum. And even what about when the derivative, let's say, is undefined? For example, if we have a cusp, couldn't that also be a local minimum? Or if I had a corner, couldn't that be a local maximum or a local minimum, right? True or no?
True.
Yeah. So the only times that we might have a local maximum or a local minimum would be at endpoints or at places where the derivative is undefined or where the derivative is 0. So that's the only places where local or absolute maxima and minima can occur. So 3 things. Derivative is 0, derivative is undefined, and endpoints. And so when I ask you soon to find the local max and min or absolute max and min of a certain function on a certain interval, those are the 3 things you'll have to check. Endpoints, derivative undefined, derivative 0. Make sense?
Yes.
Great. So those things have a special name. Places where the derivative is 0 or where the derivative doesn't exist or is undefined, we call critical points. Okay? Sometimes they're referred to as critical values also. Critical points or critical values are places where your derivative is undefined or equal to 0. Okay? And then specifically places where the derivative is 0 is called a stationary point, but it's so unlikely that they'll ask you about that, I wouldn't even worry about it. They will ask you though to find critical values and critical points. So what we're going to try to do is look for the absolute max and absolute min of x to the 2/3 on this closed interval from -2 to 3. So where can an absolute maximum or minimum occur? There's 3 places, right? Right? 3 places, right?
Yeah.
Endpoints, derivative undefined, and derivative 0. So let's find those. Well, here's the first one. There's the endpoints. We might have a local, sorry, an absolute max or an absolute min at one of the 2 endpoints. We also might have it at anywhere where the derivative is 0 or where the derivative is undefined. So let's find out what f prime of x is. What is f prime of x?
Two-thirds x to the -1/3.
2/3 x to the -1/3. Good. All right. So first off, f prime equals 0. Well, that'd be when, I'm going to rewrite this as 2/3 cube roots of x. That'd be when this equals 0. And f prime is undefined whenever that is undefined. So when does a fraction equal 0?
When the numerator equals 0.
And when does 2 equal 0?
Never.
Never. So this is never true. And when is a fraction undefined?
The denominator is 0.
If the denominator is 0. So when does 3 cube roots of x equal 0? When x is
0.
When x is 0. So we have 3 different choices for where we might have an absolute max or an absolute min. -2, 3, and 0 are endpoints, places where the derivative was undefined, and places where the derivative was 0, which were never, right? There never was one of those. Good or no?
Good.
Spectacular. All right, so let's figure out which one is the absolute max and which one is the absolute min. See, f of -2 we need to find. We need to find f of 0, and we need to find f of 3. Those are the three x values where we might have had an absolute max or a min. So if f of x, what was f of x? It was, I don't even remember now. What was it? X to the 2/3? Well, 0 to the 2/3 is pretty easy. That's 0, right? What about -2 to the 2/3? First, you square the -2 to make it a 4, right? And then cube root it. So this is the cube root of 4. And we'll do the same with 3. First, we square the 3 and then cube root it. So cube root of 9. Which of those three numbers is the smallest?
0.
What?
0.
Yeah. So it has an absolute min of 0 at x equals 0. And which one of those three numbers is the largest?
Cube root of 9.
Cube root of 9. And so on the closed interval from -2 to 3, the absolute minimum is 0. It occurs at x equals 0. And the absolute max is the cube root of 9. And it occurs at 3. Any questions on that? Or everybody okay with that? Or
Wait, so what is the cube root of 4 then? Is that like local rather than global?
yeah, that one would be a local maximum, and it's just a local maximum that happens to be at an endpoint. So if we were to, let me pull up Desmos here real quick. I can't quite restrict that. I'm sure there's a way to restrict the domain on it, but I don't actually know how to. Let me share Desmos. So here's x to the 2/3. So we can see this is what it looks like at -2 or right here. And so we're coming down here to 0 and then up here at 3. So 3 at x equals 3 is the absolute max because that's higher than it is over here at -2. -2 is just a local max. 0 is an absolute and a local minimum.
Okay, that
That's
makes sense.
Yeah, cool. All right, I was hoping to do one more because we got through one more in the other class period. It looks like we're out of time, and that one takes a little longer. So I think we'll stop there for today.